Good evening and welcome back to Vegas October 1 Sounds. Tonight we're kind of going to do a little bit of a retro review of what this channel has done and why it's relevant. And I say this because so often each video that I do is focused on one narrowly defined concept or purpose. And sometimes even I forget that what I've done and how it all fits together. But it all does fit together in a way that makes tremendous sense. And we just have to step back and see the proverbial forest from the trees, because we've been whacking down trees left, right, and center. I've whacked down, LRAD, I've whacked down speakers, I've whacked down fake sound reproducers for gunshots. I've whacked down, did I say after midnight already? After midnight shots. I've demonstrated, that the sounds were coming from one localized area and it was elevated and all that. And so we've, cut down a lot of trees. We presented the foundation for a lot of analysis, and we have started to answer a lot of the very basic questions that everybody asks about the Vegas shooting. I'll never be able to tell you who did it because that's not embedded in the acoustic information. I might, if I'm tremendously lucky one day, all these caveats there, be able to tell you what type of person was making the shooting. That is, whether or not they were healthy or not, whether or not they were strong or not, or that sort of thing. Because the way that the bump stocks work, and I think it's pretty much a foregone conclusion at this point that it was a bump stock. Haven't proved it, but I've demonstrated that it wasn't a belt-fed 240 series or a magazine-fed 240 series or a tripod-mounted helicopter 240 series in one of my papers. What most people don't realize, or maybe some people do realize, and we just tend to forget, is that if you draw a pyramid, where are we at? What have I shown in the last 60 videos? What I've shown is the tip of the pyramid. I've only shown you just small pieces of a huge repository of information and knowledge. For example, I've read and analyzed more than 100 patents. I've looked at more than 300 research papers on the topics I've been presenting. I've written more than 1,000 pages of analysis, of which, if you were lucky, you saw 100 pages. And I've created a massive database of information relating to the shots that were fired in Vegas on the evening of October 1, 2017. Has it really been that long now? Yeah, I guess it has. So, even for myself, sometimes I go back and I watch a video and I go, man, that's a good video, or man, that's could be refined a whole lot better. But remember, we're dealing with just the surface of what I have to present. And so, let's take a look at where I'm at. You as the viewer, because you've probably missed a lot of things. I know, even going back and listening to my own videos, I pick up on stuff that I said which was spot on that I don't even remember saying. So here we are in today's world, where we're talking about, let me erase this stuff off the desk before I start looking at something. In the most recent videos, outside of criticizing a few people for the lack of due diligence, I've been talking about taking videos and aligning them through visual context, and from that alignment of the videos, finding a visual event that occurs in both videos and aligning those videos to each other, maybe 2 videos, maybe 10 videos, and from that measuring sounds relative to that video alignment process, and then coming up with an absolute time scale on where the sounds occurred relative to that video event. And from there we can tell which video received the sound first, second, third, and we can rank them. And from those video alignments, we can then come up with an array of difference of times of arrival for the muzzle blast. In this case, we're measuring muzzle blast, and from that we can tell which video received the sound in what order. And then from that information, we can take that and we can do various manipulations of data, and we can start to realize and locate where the sound came from, even though we don't know the absolute time frame at which it started. So, but let's go back and look where this whole thing started, because it starts right from the beginning with this very first video called Introduction to Gunshot Acoustics that I presented. And it's the very first video I did, and it's a very complete video in the sense that it takes you from the very beginnings of things to all the way up to presenting the information in a graph, which is one of the foundational graphs of this whole channel. That let me get to it. There we go. This is a lag graph, or a lag plot graph, where you take and measure the lag. You measure the time of arrival of the muzzle blast, you measure the time of arrival of the shock wave, you subtract the difference, and that's the lag. And then you take that lag and you plot it versus longitude and latitude, and you can see where similar lags group in this contour plot. And from that, we can see that in general, let me get a nice color here. Let's go with pink. No, I said pink. There we go. That a line can be drawn right down the middle that points to the source of the sounds. And we know that because from the theory of gunshot acoustics, lag is symmetrical about the bullet path, and this line would represent the average bullet path over all these observations here. And we know then that roughly where the source of the sound is for these observations. And then also from this graph we can tell that it's elevated because this graph is not doesn't take on a V shape, let's say. It should take on a V shape if it was at ground level. That is, if all the recordings were at the same elevation as the shooter. And since it's not, it's elevated position, we don't get a V, we get this sort of a parabolic looking thing. Now that's the end result of the very first paper. And in this paper, we introduce a lot of concepts, enough concepts for people to understand what's happening. And just as a review, we introduced waveform plots, amplitude up and down, time on the bottom axis, left to right, and we talk about the density of the signals and what you might look at and count here and blah blah blah. And then we move on to the dB squared spectrogram plot, and I explain a little bit about what a spectrogram plot is and how from that waveform what all these signals mean. And then we go on to a log frequency spectrogram plot, to where we can easily identify the two types of sound involved with a gunshot. One is the crack produced by a supersonic projectile, and the other is the corresponding muzzle blast, which arrives after the supersonic cracks. And that difference indicated by this little arrow here is what we call the lag, and you can measure it for each one of these. What are there, 8 shots as I recall? 1, 2, 3, 4, 5, 6, 8, and you can measure the lag for each one. And then that's when we plot them. Oh, I covered one more graph, which was the spectral contrast, which is sometimes needed because not all audio is as clean as this one, and the spectral contrast gives you another way of looking at this data. And then from all that, oh, I forgot about that. Well, eventually we'll end up with that lag plot, but in the meantime I said that once you've measured the muzzle data, that is, you've measured and marked each of the points in time of where a muzzle blast occurs, you can subtract the difference in time and come up with how much time there were between shots, and then you can do the same thing for between the deltas and come up with what the change in time between each round was, and you can also calculate the revolutions per minute. And then you could do a similar thing for shock waves, although it doesn't have as much meaning. And I go on to explain a lot about what you can interpret from that data. And that's just in the very first video. Well, we've had a lot of hours between that very first video and now. And we've covered a lot of topics, and there are many topics left to cover. But let's take a look at some of the information that's being presented and tie it together. You know, this very first paper covered predominantly how to go about collecting the data with a little bit of interpretation. And nowhere in that first paper do I say how you calculate the distance to the shooter or how to isolate the shooter location on a map. And that's what we're in the throes of doing right now, is explaining how, given these time of arrival differences, as I was just talking about in this table, we can come up with a fairly good idea of where the sounds came from. But between that first video and where we're at now, there's a whole bunch of other information that is available to us to determine a lot of different things. And all of it ties together. None of it stands by itself. None of it has the whole picture by itself. For example, in our throes of calculating these time difference of arrivals, we have established the order in which these videos received the sound. But that tells us nothing about and we did this for one shot only, namely the first shot of the second burst of Volley 9. Well, there's more than 1,000 other shots that have yet to be analyzed in a similar way. And in doing that, you're going to end up with massive amounts of analysis to perform. And then there's going to be ways of aggregating all that analysis into one or a group of numbers that will give you the answer to your question in a way that's maybe very clear or maybe not so very clear. One example of not so very clear is what's the exact position of the shooter? Well, based upon the algorithms that I've currently demonstrated to you, you cannot isolate the shooting location down to anything more precise than plus or minus, probably at the best 100 feet. And I'm giving that a little bit of a margin of leeway and saying, a sphere of diameter 200 feet. But a more precise piece of analysis and data that we can assert is based upon those muzzle blasts. For example, here we talk about 1, 2, 3, 4, 5, 6, 7 different videos containing that shot in the second burst of Volley 9. And if we go to just the let's take and look at one way of looking at it. This one. Okay. This graph measures and plots those muzzle blasts for the entire burst. And in this case, there are 71 shots in the second burst of Volley 9. And I've measured each shot in each of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 videos for 71 rounds each, so it's 710 individual muzzle blasts that I've measured from these videos, and I've plotted them in time. And what I did was took the first shot, which is the shot we've been talking about, and said, okay, this is where everybody starts. Now that's ignoring the delay in time of arrival due to distance. And so what this graph is saying, or what question you could answer is this the same volley? And the answer to that would be yes, if all the muzzle blasts line up. Because as you well know by now, the muzzle blast preserves the order of timing between rounds. Unless, something's moving. So, for example, you have to have a static source and a static observer. Namely, the shooter has to be in one spot and the recording has to be in another spot, and for that entire volley. And then across all 10 videos, and then all the muzzle blast times would line up. So let's take a look at this graph. Now, in this graph, of course, we have, I'm going to list these things. We have the Oasis Apartments. We have the bus stop in front of Mandalay Bay. We have CopCam batch 9, number 72, CopCam 34, Underbar, similarly batch 34, number 11114. And then we have the Goodwin video, which occurs over there on the south side of the portico to the entrance to Mandalay Bay. The Raymond Page, and he's near gate 2A, the southmost gate 2 when this occurs. And then we have the Corey Langdon video, and we have the ladies that are in front of the Luxor in the parking lot that are speaking Hebrew. And then we have the video from the Excalibur, on top of the Excalibur Hotel. And then also we have one video from down in the venue, just middle stage but under the stage. So we have all these 10 videos, all their muzzle blasts measured. And if they line up, then they are all the same. Now you can immediately see that some things don't line up. And the question becomes why. But overall, they all line up pretty good. So from this graph, we can assert that they were all measuring the same sound. Whether or not they're from the same source is a slightly different question. But if they weren't from the same source, then somebody would have had to duplicate these down to the millisecond, which is a very hard thing to do. Because it's not just a matter of taking a tape and plugging it into several speakers. You have to synchronize the speakers down to the millisecond. And that's hard to do. Particularly across as many things. So anyway, assuming then these are all from the same source, and I believe they are, and we can determine that by coupling this graph with the work we were doing over here. Because of the time of arrival, there is no indication of any source of sound other than a single point coming from a direction that is southwest of the venue from all these numbers, because they all line up in terms of the delay being appropriate for that position. Had there been somebody on the west side of the venue, all these numbers would have changed for the observations, and it would point towards that source. So you couple this with this, and you could make some pretty good inferences. Namely, even though our aligned videos don't include, say, Corey Langdon at the moment, or the Goodwin, we can pretty well assert that they're all measuring the same thing, and that they're all coming from the same source on these two stuff. Now in here, you can see that there are slight differences. For example, the pink line here near second 4, it has some difference in alignment, which is one of the cop cams down in the venue. And in this case, it's very likely that he was moving around. Let's see if we can find some other difference over here. Yeah, up here on the orange one, which is Raymond Page, he was doing some slight walking during this, so you see a slight misalignment. And this, what I was trying to get to, is this is a very precise measurement. That is, each muzzle blast is measured down to, roughly plus or minus 1 or 2 milliseconds. And since each of these lines is about 100 milliseconds apart, then these small differences are on the order of 10 milliseconds, which might correspond to about 10 or 20 feet movement. But what you can see is that narrows it down far more precisely, the movement that is, than asking where the shooter is located, which is in a sphere of sphere of diameter 200 feet. So depending upon the nature of the question you're asking and the nature of the data, you can get both very precise and not so precise answers. So if I wanted to know, well, let's ask a real question. Here is the Oasis. The light blue on the bottom is the Oasis Apartments recording of these muzzle blasts, and we know from watching the video that that person may turn a little bit, but he does not move much forward, backwards, left, or right. Therefore, we can use that as a base reference and compare it to some of these other things. So, for example, if we were to drag this little line here, which I've provided across to, let's just pick one that's on the bottom, the blue. If we line it up right there, then you see the width of that line has covered every spot up and down on that. So for all videos, that round occurred in the same time frame as all the other videos. So just for that round, you can say that, you know, they were static relative to one another. And you can apply that same technique everywhere else. The big bold lines are just every 10th round. I just did that so you could see easily. And so you can see in some places where, here's one over here. On the orange, which again was the bright orange, Raymond Page, over here on the, let's see, what's that, 1, 2, 3, 4, 5, on the 6th, 7th, and 8th shots, the time delay between rounds increased, which means that he was walking away from this source of the shooter, thereby increasing the delay for 3 rounds. But then on this one, which is the 9th one, it lined back up, which means that he must have reversed his direction and come back to a spot which was originally close to where he started. And that's the type of stuff you can tell. You can tell very precisely who was moving and approximately how far they were moving and approximately in what direction. So when you put 10 videos together, there's very little that will escape observation in terms of their relative positions. And that's the power of multiple observations when you have a lot of precise measurements. Because collectively, this forms a grid where you have put a stake in the ground and tied a string between each of the other observation points. And if any observation point moves, then there's a lot of strings that are going to be tugged on that you can notice, or slacked up, and you can notice that. And that's what this does, is tugging on it. You could ask, where does this all fit in the big picture? Where does this Volley 9 thing fit in the big picture? And from the muzzle data, you can tell, and you can plot out a graph of where all these things are. This one is Volley 9 over here, and the time scale on this starts roughly at Volley 1, not at the first shots, and Volley 9 occurs roughly at about 400 seconds after Volley 1. And so in this case we have 1, 2, 3, a partial there, 4, 5, 6, 7, 8, 9 videos that are measured and displayed on this graph. And so you can see in the big picture where Volley 9 is, Volley 9 A, B, and C are. And similarly, all these other things. And these are graphs from, probably a year ago. But it's still relatively accurate today, even though I do need to go back and generate them. But this is the big picture. If you wanted to know where Volley 9 went, that's all from measuring all those muzzle blasts. Just another piece of the puzzle. And in this case, if you wanted to look and say, well, what were there gaps between volleys? Since this plots everything in absolute time, you could count these little 5-second. I think they're 5-second. Yeah, 5-second. You could count up the number of lines there and say, well, let's pick this one right there. And since there's 1, 2, 3 plus, then there's about 17 seconds between this volley and that volley. And so this gives you a nice little picture to ask various questions like, what the heck was going on over here between volleys 10, 11, and 12? I mean, there's this huge gap compared to all these nice regularly things over here. In fact, this one right here between volleys 1 and 2 is substantially larger by a factor of 2 than the gap between volleys 2 and 3, which is the gap between 2 and 3 is similar to the gap between 3 and 4. And so that sort of represents a modality there of minimum distance between gaps. And then this one over here represents a different modality, which you could infer that something else was going on. Similarly, you could infer that this modality, or size of the gap between these, corresponds roughly to that. This one a little bit larger, and that one I'm just, somewhere in between. So these 3 or 4 volleys here were probably done in sequence in a manner similar to these volleys over there. But the gap here is different. The gap there is big. The gap here is a little larger. Blah, blah, blah. So you could ask questions and perhaps draw some inferences from this large picture. Another piece of information derived from a global perspective on a similar basis would be this graph. And this graph takes the time between each round and estimates the rounds per minute being fired and plots it. And so it's not real revealing in the sense that there's such a large time frame covered, 10 minutes, that you don't get a feel for each volley and what it's doing. But what you can see immediately is that the rounds per minute varies radically in almost every volley, with a few exceptions. For example, volley 5 right here, parts 2 and 3, are pretty narrow. Here's volley 1, with the exception of these outliers at the very start and a little bit at the end, is a pretty narrow region that sort of is climbing over time, and that all of these volleys tend to center around 600 RPM. Some don't, and these single shots obviously don't, which are here and here, because the time between each round is huge and therefore the RPMs are small. That's the type of information you can get there. And you see all this starts to pull together and paint a picture from a global perspective and a minute perspective, and you can ask lots and lots of questions. It's not just determining the shooter's distance. It's all these things. And that's what careful research can provide. And we've got more in here. If you wanted to... let's say, well, this one is another global perspective one. And in this one, it's just the inverse, where I measure the RPM directly rather than plot the time between rounds. And it's kind of skewed in that all these graphs down here are the volleys, and they look small, but they only look small because the single shots have skewed the scale so dramatically. And so that one's not quite as useful. If we wanted to look at just volley 9 again, we could. And we could pull up a graph which plots things in absolute time, and this is just volley 9B, which is the middle burst of volley 9, and this plots it such that the time delay is preserved. And so we have 1, 2, 3 videos here which start at a separate time, and I haven't resolved that yet. And so either I have miscalculated something, or there's a phenomena causing these to start later. So let's see, that's 34 underbar 114, the red one is 9 underbar 72, and the pink one is taxi. All of those probably have this in it because they moved relative to these at the start, or they moved after the last volley and before this one. So that's what we can tell. If these were all perfectly lined up, then there would have been no movement during the volley and prior to or after. Actually, you couldn't tell after, but prior to. So, this plot depends upon what happened before. So, everything from let's see on the taxi. Let's pick one, Oasis, for example. Oasis is the dark purple up there and lines pretty well with all these, and it starts with volley 7. That's the first volley that's recorded. So for this one you have volley 7 and 8 prior to 9, and this graph says that for all of those volleys we didn't lose or gain any time relative to volley 9. And similarly for all the ones that line up exactly, but we did on these 3. So that probably means, not conclusively just from this graph, that they were moving relative to some of these other positions which were not. Alright? If we wanted to look at volley 9B. Now this one is from the ladies in front of the Luxor, and this is called a stem plot, and rather having those little squiggly lines, we have up and down lines representing the change in delta from 0 from shot to shot. So across here, these are shot numbers. There's 71 shots. So this graph is evenly spaced with respect to shot numbers, and then the difference from the previous shot, i.e. the delta, is plotted up and down. And so this gives us a graphical indication of how much variance was occurring between the rounds. And so from this one you can see that for more than half of the volley, the difference between the deltas were on the low side, and for the other one they were on the upper side. And so that would tend to indicate that the volleys were not consistent between the first and the second half, but were probably decreasing in RPM. I hope I got that right. Alright. And then if we took another chart, essentially the same information, although we have parts A and B. So here we have the entirety of volley 9, only this time we plotted the delta T rather than the RPM. So this measures directly versus absolute time relative to the start of the video, what was happening with the time between rounds. And this is a very informative graph because it shows clearly that the first few rounds fired, then a gap, then 71 rounds, and then a gap. They all have kind of different things. The first ones were way all over the map. All over the map. They varied by 50 milliseconds peak to peak. Whereas these probably only varied, let's see, that's 25, maybe about a total of 35 from the slowest to the fastest. And similarly over here, these are probably about 40 from the slowest to the fastest. But along the way, they remain fairly stable, whereas these are completely unstable. And so there were different pressures and forces acting on that bump stock. And you know, the pressures were you have to hold the bump stock forward, and you have to hold it not so tight that it can still oscillate or overcome the recoil from the gun. And so this might indicate something about the physical characteristics of the shooter, or you know, maybe they were different. I don't think so, but there could have been different rounds loaded for those first 7 that, you know, had a larger recoil, or just any number of factors. But it starts to narrow down some characteristics about how those rounds were being discharged. Here, where they're very, very close in time, indicates that whoever was firing the gun had a very precise control on the discharge rate for a vast majority, although it tended to, you know, creep up slowly, which means it slowed down slightly in that part. And over here, when it started back up, you know, it's kind of interesting that these two started at quicker times and then gradually got slower. But they both come back to 0.1 or center around 0.1 seconds between rounds, which is 600 RPM. So this, you know, after you look at a lot of the others, this one is the middle part anyway, is pretty stable. And that's starting to approach some of the types of graphs you might see with a machine gun. Whereas this one over here is clearly not a machine gun. unless that machine gun is just, well, there are some machine guns that do exhibit that type of behavior, but they're not in common use today. So that would be looking at up close on, not real up close, but it's kind of up close on Volley 9. Let's see what I have here. Here I have plotted 3 different videos for Volley 9B, and there's actually 3 there, but 2 of them, the green and the blue, are so close that it's hard to distinguish them. And what this does is it plots the time between rounds versus shot number. So along the x-axis here, we have evenly divided things in time, essentially, even though it's just shot number. And then we say, so therefore the amplitude of this wave is proportional to the delta, or the difference in delta. And so now you could ask a couple interesting different questions here. Why are the green and the blue ones extremely close together, but yet the orange one, which is the ladies in front of the Luxor, different and almost complementary, although they all follow the same, approximate rate, and they're all both very stable. There are minor differences. Now, when you understand that what you're measuring is the time between rounds, if you measure one round and it's off, if it's off one direction, then the previous delta is going to be off in the opposite direction. So they come in pairs, and that's why here you see that there's a big jump. This could be caused by the fact that this point right here was incorrectly measured by 1 or 2 milliseconds, and therefore it threw this one off by the same amount and this one off a little bit too. But if it were a perfect world, then all these lines would be identical and you'd see but one graph. It's not. So this gives you some more information also, but it probably reveals more about how I measured them than how they're recorded. For me, this represents, graphs which are equal, except for this one little spot over here where I don't understand why there's this tail end stuff there. Because all of them, were 71 shots long, and yet I see a little extra crud there, which I don't understand. So perhaps my algorithm made a mistake, but I'd have to go back and review it. Alright. Let's see, is there any other graph that I haven't covered? Oh yeah, here's one. And by the way, I have more than 150 graphs that are available to me that I've programmed up in custom software to look at various characteristics of all this data that I have. These are focused on muzzle blast, but I have a correspondingly thing for the shock waves, but the same graph that you use here would not reveal any similar information for this shock wave, because it's a whole different set of physics, whole different set of timing, etc. So what am I trying to say here is that there's lots of things to look at. It's not just what we're doing in the current video. It's not just these aligning things and coming up with a distance. There's tons and tons and tons of other information that can be useful. Now in this graph, which I find to be essentially useless, and that's the way that some of them end up being. Some of them for most of your analysis become useless, but then all of a sudden out will pop this big glaring thing on those mostly useless graphs for one video or one sound or one round or something, and it tails a tale that needs to be told. That is, without that graph, which is mostly useless most of the time, you would not see that type of information, and that's what this kind of graph is. What we have here is Volley 9B, the 71 shots, and we have plotted them in video time, which means relative to the start of the video, and they're unaligned. So basically this is saying how well do the videos agree in timing. And as we can see, there are 3 different videos, and they don't agree too well in timing, even though the difference between these are only 50 milliseconds. And there's number of reasons for that. Some are obvious and some are not so obvious. But if you had two videos which you expected to match up identically and these lines didn't match up, then this would be an extremely valuable graph. But in this case, since the videos don't start and stop at the same time, this is to be expected. Alright. And then, these have all been kind of superficial graphs. When you get down into the deep bowels of what needs to be discovered and you're asking hard questions, then you have graphs like this, which actually are composed of 10 graphs in one, and what it shows is a very deep set of information on a small region of data. And in this case, it's from the under video, which is that region near the front of the stage, under it, in the middle. And these are for those 6 booms that we hear, and I wanted to take a close look at the 6 booms and see what was happening in there. And so the 6 booms I've marked in my data, which are indicated by the blue triangles here. And up here, this was just a couple of different algorithms where I was trying to detect shock waves. So they were trying to detect these peaks up there, and in this case, that's kind of irrelevant. But nevertheless, the algorithm was calculating. Here's the waveform plot where I've marked out the separation between booms in seconds and counted the number of booms. And let's see, 1, 2, 3, 4, 5. The 6th one must have been over here to the left or to the right. To the right. Then I would do some special processing, which would separate out the foreground from the background, the harmonics from the percussive, and then I would show various aspects of it. So here we have the background, which would be those noises which aren't quite so loud. And then you would have the foreground, which are the noises that are loud. So you can see, well, that's another video. And here's the same thing for shock wave frequency stuff. So you can see that there are several different sounds in there that are shock wave in nature, but they aren't, because I know there's no shock waves there. And then we have, after we apply a filter, what the signal looks like compared to above. See, there's the signal with these peaks in it indicating those booms, but after I apply a filter that eliminates low frequency or high frequency stuff, then it kind of looks like that. And then if I wanted to detect just those percussive, those peaks, then I would apply a different filter and we get that. And then if I wanted to look at the things which weren't percussive but were harmonic, then the signal would look like that. And so, this gives me several different graphs to look at from which I can garner other types of information. And sometimes it's useful, sometimes it's not. Sometimes it's, misleading, sometimes it's not. And so I measure, this is the type, when I get down to this part, that I typically use, where I'm looking for real clear indications of muzzles. And in this case, the booms kind of look like muzzle blasts, but they have the wrong timing, but they have the right similar of frequency. And this is, what I would get after applying all those filters to the original signal up there. Let's get it up there. That's the original signal. And down here, after applying a bunch of massive processing, we end up with a fairly clear picture of the timing of those various things without all the background crap clogging up the works. And so these are the 3 that I would typically be focused on when I'm asking the question, when did an event occur? They don't show you the frequency, but they show you when. Alright, so that's just another type of graph, and that's a very complicated graph, both to implement and interpret. And then after all that, it brings us right back to this graph, the lag one, which is easy to interpret, easy to gather, and is very revealing, but it's not very definitive and precise in terms of where the shooter is or blah blah blah. And then, as if that's not enough, I have an Excel. The program generate me a workbook, an Excel spreadsheet consisting of quite a number of worksheets. And in that worksheet, I have lots of other information. Now remember, this is a run that occurred about a year ago or so, in which I have lots of different things I can do. The most frequent one that I go to is an extensive timeline thing on where I can go. Let's say we pop down to 9B we were looking at, right? Then here we can see the 9Bs which start on that one, and in here, and we can look at them. Oh, they're all the same number. They all measure the same number of rounds, which is good. We can look at their duration. I think that's duration, isn't it? Sometimes I forget. Nope, that's the gap. Column E was the duration. Column E, which is duration. And they should all have the same duration. And as you can see, they're varying by 10, on the order of 10 milliseconds. Over here is the RPM in column J, and there's a whole host of other parameters over here. Particularly, this one is the average of the time between rounds, the average delta T between rounds, and this is the standard deviation, which is a statistical measure of variance. Okay, and then if I wanted to look at just, there are a lot of different ways of using this. If I wanted to look at just the 9B volley, then I'd go down here and I'd locate it and click on it. This is a hyperlinked worksheet, and we'd have just those videos containing 9B and then just that information that I was just showing you. And you could look at it in a reverse way too. You could look at one. Let's go, for example, if we wanted to look at just the thing from Goodwin, so we wanted to compare all the volleys in Goodwin, then the volleys in Goodwin would be 8B, 9A, 9B, 9C, which is not very much, and we get that same information there. If we wanted to look at Oasis, for example, Oasis, right, the Oasis Apartments, and then it carries 7 through 10, and there's a bunch of other information in this worksheet. And these are just some of the things that are available when you're doing the research from my perspective that I haven't really focused on a lot. I've created a video on each one of these explaining superficially what they mean, but you have to use them all to paint a big picture and verify your work. It's not just determining or answering some fundamental questions, but it's all the pieces in between, from identifying what the sound is, whether it's a muzzle blast or a shock wave or a horn or something else like that, all the way right up to the bigger questions, which is how many shooters, where were they at, what were the distances to the shooter, what type of weapon they were using, what was the caliber, all those things. There's just a ton of measurements and recordings, and that is what it takes to perform acoustic gunshot analysis. You don't just get to pick one thing from one video and claim success. It doesn't work that way. I've tried that probably more than 1,000 times, and every time I've been disappointed. So, yeah, I haven't published any of that kind of crap, generally speaking, but, we're all excited, and we all sometimes think that we found the smoking gun, but in reality, after you apply this type of analysis with a massive number of measurements, the excitement tends to get, mediated down. Alright, so what am I trying to say with this video? I'm trying to give an overview, just a sort of a recap of the massive amount of stuff that has to be done to do the job, to answer the questions in a way that is reliable and accurate. And that's what we're doing on this channel. And it's you and me, because I get feedback all the time. I get, just like Scott turned me on to the fact that the LRAD devices have a very limited frequency response, and I hadn't plugged that into my brain, And when I did, and I went and looked at that, there was a big, oh yeah, aha moment that says, oh, of course, that would completely exclude LRAD from being used that evening if you understand what a limited frequency response means. And so, I think that's pretty much all I wanted to say tonight. For those that are new, kind of newish to the channel, there's just a ton of information. And I do need to go back and organize and index it in a way that makes it more accessible if you wanted to just see the videos on muzzle blast measurements, or you just wanted to see the video on shock waves, or Doppler effect, or all these other things that we've covered. There really does need to be a table of contents and an index. But YouTube, unfortunately, isn't very cooperative in that regards. They took away the ability to hyperlink between videos, which would have been the primary way to do that sort of thing. But I'll figure out a way somewhere, and we'll grab you in the next one. Have a good evening.